The rule set said to align your coordinate system with the acceleration. But the acceleration is got to be this way, towards the center. So you have to break the tension up in such a way as to have a portion of the tension towards the center. That's the part that's causing centripetal motion. And part of the tension upwards, that's the part that's keeping the stopper from falling to the floor. So without doing the math, because we don't have the time, T sine theta is this way, and T cosine theta is that way. That good? Now it's the part of the weight that's towards the center that is causing centripetal acceleration. And you have a way of finding out what that tension is. So there's things you can put together here, but also you have to realize as well that the radius is also a portion of the length of the string. You never measured the radius, you measured the length of the string. Okay? Now you can bring these pieces together, sure, most certainly. Now, I'm going to leave this kind of here and not go on with it very much. I've given you the basic pieces for this problem. Your job is to now take these basic pieces and see if you can figure out how the angle affects the answer. You have quite a few pieces to choose from here. So I'm going to encourage you to consider a few things. Consider a relationship between the mass of the stopper, the angle, and the mass that's hung. There's a relationship there. Look at it. And look at the relationship between the portion of the tension towards the center and the centripetal acceleration. I'm asking for both of those things to be done. So let me explain it again. T sine theta has to equal the weight of the stopper. Tension also has to equal the weight that's hung. And T cosine theta has to equal the mass of the stopper, omega squared, times R. Those are all the same pieces as before. I'm just putting them up there again. The only difference is that we now have net force in the y direction, that's this. Net force in the x direction equals MAC, that's this. And this one's just net force in the y direction. But that's all I want to say about it. I want you guys to take this and look at it as part of the homework question related to this. All right? We have 10 minutes left. There is something new that I need to talk to you about. Does everybody have a good start here? I didn't say a handle on it, but a good start. So take this home, take a better start at it. If you don't know what direction you're going, I'll be honest with you. See how you can work the angle into your answer. How is the angle related to the spin rate of your stopper? I want to see if you can find that. I don't want to leave you. I gave you lots of stuff here to work with. Take a look at it all when you go home. I want to talk about something else. And this is kind of the last canned problem for uniform circular motion until we get to gravity. When I mean canned, there are specific problems that always come up because they're good examples of where centripetal motion is kind of part of your daily life. And so this is the one where I think that you'll have some of the most difficulty with, but I think it's also kind of rewarding. Who's ever grown up north at all? It snows there, right? Now, in Florida, we pitch our roads in the middle, so the water will run out. And in most places, they pitch their roads that way, so that even if you have snow on the road, when it melts, it'll run to the sides of the road. Now, That doesn't serve us particularly well because if your road is pitched in the middle, it's actually making it more difficult to drive on the road because it's always at an angle. Have you noticed, though, that there are places where we bank the roads purposefully, not to get the water to run off, but to make it easier to make a turn? Think the on and off ramps to your major interstates, the knot of roads over by the airport. In those cases, the roads are banked. And the reason they're banked has to do with what it takes for a car to make a successful turn. And we've already had this conversation. Let's review. For a car to make a successful turn, and 6 period was ruthlessly mean about the car I drew. I mean, like to the point where I was almost in tears. So I'm expecting you guys to not be as mean as them. If my car is going this way, it would have to experience an unbalanced force. What direction would that unbalanced force have to be in order for the car to stay on the road? Left, right, up, down? Yeah, I would have to have an unbalanced force this way. What would cause that force? Yes, sir? I don't think so. Let's look at the car from the back, and maybe that will help. Because if here's the road surface, and the turn goes, in this direction, right? You guys see what I'm trying to draw there? And the car is, all right, I'm going to do a better job on my car this time because I don't want to be made fun of. The car. And then the car has a bumper. It's the bumper of the car. And then there's the kind of the trunk area of the car. And then the window. There's lights and then Is that a car? It's beautiful. Thank you. Thank you. I'm going to work on my cars, but I have to get them up there really fast, and I am not an artist. If this is the car that's trying to make a left turn, it can't be the normal force that is causing that to happen because the normal force in the car would be straight up. It has to be, from the floor. And, of course, weight's going to be down. So we know that we turn tires. It's the frictional force that causes it, right? Friction has to push the car in this direction. And not just any friction, static friction. Now, we did this already. It's in your notes. So I don't want to spend a ton of time on it, but just a couple of reminders that the net force in the x direction equals MAC, because we're turning. That is related to this velocity here. How fast is the car going? The tangential velocity, right, Zach? Yes. Excellent. So when I'm considering the unbalanced force here, I'm really interested in this formulation. Right? The car's speed as it goes around the turn divided by the radius of curvature. And we think that this force is going to come from the static frictional force. Well, static friction has a limit. The next thing you have to always remember. Static friction has a limit. It can be any value up to a limit. It's an inequality, that's tough. And I know that dealing with the inequalities is hard. But if the car is on level ground, the normal equals the weight of the car. This gives us something we can bring together. We can put the normal in here. We can put the friction here so that we are always substituting into the inequality. And we get m v squared over r is less than or equal to mu s mg. Tells us a lot about what it takes for a car to make a turn. If we cancel out those m's, we see a distinct relationship that has limits. I can go faster if I have stickier tires. It's not like you can change gravity. I could go faster if I make the radius bigger. That means defining your own road, perhaps, or drifting into another lane. Or look at South Mobley. How many people drift off the road? It's a lot of them. Another way to do this is to help the car. You don't have to turn this way. You can help the car through the turn. that's banking the roadway. Now, if you live up north, they bank the roads a lot more, but even in the south here, we bank on-ramps. Now, the truth is, we don't bank them as much as I'm going to describe. They're banked a small amount. But if you've ever been stuck on a freeway, on the banked portion of the freeway, it can feel pretty steep. The idea is that if you bank the road, you might not need to rely on friction to make the turn. So consider a banked road surface. And again, this is going to be hard for us to kind of picture. So this is the top-down version of the road surface, where your car is trying to make this turn. And I gotta draw a car again. I'm going fast because I know the bell's gonna ring, and I'm scared. It'll scare me. Oh, this one's worse. Brake lights.
Believe in yourself. You can do it.
Thanks. I knew you would trust me. Yay! It's a car. All right. So, in this case, I want you to think of it this way. What if you're trying to design a road where no friction was necessary to make the turn? Okay, so we're gonna go in an extreme case. So this whole thing is frictionless. Now, right now, the car just sitting on this road surface, if it were truly frictionless, the car would slide down the ramp, wouldn't it? If it was truly frictionless. However, if the car is moving forwards, if it has a velocity in this direction, then it has inertia going around the turn. And an unbalanced force will be necessary for it to make the turn. I don't expect you to know this, so I want to speak about this. There's only two forces acting on the car if the car is on a frictionless incline. There's the downward force for weight and the normal force from the road surface. Under these conditions, a part of the normal force is keeping the car from sliding down the ramp, and the other part of the normal force is causing centripetal motion. It's not obvious or clear, but remember, there has to be an unbalanced force towards the center of motion. And I know so far this year, whenever we've had an incline, I've told you guys to make the incline the horizontal direction, but not here. We want the acceleration to be in this direction. That has to be the direction of the acceleration. That is the positive x direction. Which means you're going to break the tension up into components. There will be the tension that balances the weight of the car, T cosine theta. Yeah?
Would that be normal or would it be tension?
I don't know why I'm saying tension. But it's good to know you guys are paying attention. Oh! It's good to know. Good to know. All right, just one more statement, then you guys can take off. It is this component of the normal force that's causing centripetal motion. Now, just real quick, n cosine theta has to equal mg. N sine theta has to be m v squared over r. Do you see something you might be able to do here? I would encourage you to take this home and get rid of the n between these two things. When you do, you get the angle that you bank your roads at. All right.